geometry and gauge theories. And we already have seen at least a couple talks where Chern-Simons term figured prominently. And as you know, that's one of the most important developments that has affected a lot of aspects of physics, especially geometry and low-dimensional topology, in the connection between math and physics. So we are very pleased that Jim agreed, taking some time off from his busy schedule, to give us a talk about the origin of Chern-Simons.
Okay. Well, I first want to say that this is a talk designed for physicists. In that, and only in that, I assume they don't know all the math that I'm going to display. However, they may well. The mathematicians certainly do, and I recommend they either leave or doze. Doze. So, there's a lot of the stuff. I want to try to get at how we got to these terms, why these so-called Chern-Simons terms, how they arose, and why they're important. But to do that, we need to start at an earlier stage. So I'm going to start with the Euler characteristic of a manifold or space. So we're going to call chi of x the Euler characteristic of x. And for a simple definition, I'll say it's the sum of the odd Beatty numbers. B sub I. So probably you know what the Beatty numbers are. Alternatively, and the way it was originally...
I doubt that everyone knows what the Beatty numbers are.
You think everyone doesn't know it?
I can tell you I don't.
Do you know Beatty? You know? No. Okay. Bi is the rank of the ith homology group. And if you want an even simpler definition, it's if you take a simplicial complex like this and you count, well, if it's two-dimensional, you would count the number of faces minus the number of edges plus the number of vertices. And in general, you could just take the alternating sum of all the numbers of all simplices of different dimensions. So you take the number of k simplices minus the k minus 1, so on. That's the Euler characteristic. Obviously, from this definition, it's a topological invariant, because the homology doesn't depend on how you know, the homology is number of holes of a certain type in various dimensions. So it's a topological invariant. This does not make that clear, the second definition, but on the other hand, it's a nice theorem, but that's true. But I want to state a theorem that's due to Poincare and Hopf. So I think I'll try to work on this board a little bit. And this is a very famous theorem. So suppose you have some closed manifold, and it's smooth and so on. Turns out you can always make a vector field on this manifold with at most a finite number of isolated singularities. See, there's one right there. See, this vector field doesn't know where it's going right here. But you can, the number of such points is finite. There's a finite number. You can do that. Never mind why, but you can do that. You can do that. Now, each one of these has not only a singularity, but the singularity has a degree associated to it. And why is that? We'll blow this singularity up here, this particular one. And we'll note that any such gives you a map of the sphere surrounding this thing into itself. So, this point and this, well, so you look at you look at this thing as it marches around the sphere. Let's put it marching around the outside of the sphere for a moment. Out here, out here, out here, and out here. Now, so you map this point to actually itself. This is the identity map. But if it pointed in, it would be halfway around, and if it curved around as it was going around this sphere in different ways, it would give a map of the sphere to itself. So you always get a map of the sphere to itself, and that's called, it's called the degree of the singularity, and so these are mi. This is the degree of map. And well, the degree of the map, yeah, it's sort of a number of windings. But of course, this is a sphere. It could be at any dimension. But goes over itself. A nice such just in the 2 dimensions is something that starts out like this, ends up like this. Over here, it's here. Over here, it's here. And it sort of slides around halfway. It's tangent. Over here, it's tangent. And I think, let's see, I guess over here, it's tangent. And what this one does, this singularity, it flips the circle around. So that has degree -1, you see, because it holds these 2 points fixed, it reverses these 2, it flips the circle. That's an orientation reversing. But this could have been a much busier vector field. It could have wrapped this circle around itself in either direction a lot of times. So that's the degree, okay? And theorem, which is due to Poincare and Hopf, is that the sum over I of the degree of mi, just the sum of the degrees, no alternation because there's nothing to alternate, is equal to the Euler characteristic of x. Now that's a beautiful theorem, and it's not obvious. You can't say, yes, of course. It's not obvious at all. There's a proof, there's an outline of a proof in Steenrod's book, and where you can take a simplicial complex and subdivide it a couple of times and then make a vector field, and then you can count with prescribed singularities, and you can count their degrees and see that you really get this edges minus faces plus vertices and so on as a result. So that's a proof. But, yeah.
The Euler character can be negative. You just take the absolute value of it?
Sure, it can be negative. What's wrong with that?
Well, but the left-hand side is positive.
No, because the degrees could be negative.
Sorry.
The degrees could be negative. Orientation reversing map, so the degrees could be negative. Yeah, the Euler characters can be anything you like. I mean, any sign that you like. And everyone, it's standard that the ordinary 2 sphere has Euler characteristic 2, and the torus is 0, and every time you add a handle, it drops by a -2, and so on. So here's this great theorem, and we're going to use this theorem to prove another great theorem. So, or it's going to be used. So So now I'm going to have x is closed. We'll just make this two-dimensional, oriented, two-manifold, two-dimensional manifold. In fact, and Riemannian, has Riemannian structure. And in deference to the physicist, I will call the curvature F. See, this is usually it's not called F in mathematics parlance, but we'll call it F. So a wonderful theorem called the Gauss-Bonnet theorem is that if I take the integral over x of 1 over 2 pi curvature, I get the Euler characteristic of x. Okay? I mean, there it is. Now, I'm going to sketch a proof of this using that. And then we're going to go to higher dimensions and look at Chern's great proof of the generalized Gauss-Bonnet theorem. And therein lies the first hint of one of these Chern-Simons forms, or whatever you want to call them, because those forms existed long before my name got attached to them. So I don't know. Anyway, there it is. So let's look at how one might prove this formula. So we'll choose a vector field. Choose a unit vector field. V with isolated singularities. And orthogonal complement W so that V wedge W is oriented. Okay, so all I'm doing here is picking a framing. There's V and there's W. And they're hopping all around here, it's moving around, except that one place it gets all confused. Let's say this particular place here, and it doesn't know what it is right over here. It's a singularity. Okay. So now let's look at a one form, A of x, which is just the covariant derivative in the x direction of the vector field V, and you dot that with W. So that's connection kind of thing. Just, yep.
So I think on this one, it's crucial that we show that the singularities are always isolated.
It is crucial.
Okay, but you didn't say that.
You can, I said you could always choose, you can always find such a vector field with a finite number of singularities. A finite number means they're isolated. Right. Okay. But if I didn't say that, I should have. So here's a differential one form, AX, and note that its exterior differential dA is equal to F. Okay. So this is really the connection form, if you like, and in this very simple case, its differential is curvature. So now I'm going to integrate. Here's what I'm going to do. I'm going to integrate F. I guess I have to take 1 over 2 pi. Yeah, okay, 1 over 2 pi F. I'm going to integrate this over x. Well, I might as well just integrate it over well, to do this, I'm going to excise the, so I'm going to, well, okay. Here, let me write up here for a minute. So here's a singularity, mi, and I'm going to let ui up a t equal the ball of radius t around mi. So before I write down this integral, let's just look at this sort of Swiss cheese thing that I've created. Here's the manifold. Here's some singularities. Here are these little balls, little disks around them. Okay? Perfectly clear. So now I can say, okay, the integral over x. Who buys the chalk around here? Morgan. I'll approve an expense for stronger chalk. Okay. So we can subtract. So the integral of 1 over 2 pi f over x is equal to the limit as t goes to 0 of the integral, the same integral, but it's going to be over x minus these balls, the collection of ui up a t, right? So I'm going to make these balls smaller and smaller and integrate over what's not there, and I'm going to integrate 1 over 2 pi f. But of course here it's dA, so that's going to be the limit as t goes to 0 of the integral of a over the boundary of this thing, x minus this collection of balls, right? And if you, now the boundary of this collection of balls is a collection of spheres, or a collection of circles in this case. So this is really equal to the integral of now a over a bunch of circles. So what do we call it? S up a t sub I over the set of circles, right? Because that's the boundary of all this, is just these circles. And limit as t goes to 0. And it's not easy, it's not difficult to see at all as you integrate this around a circle. It's nothing but the degree of the vector field. So this is equal to the sum of the degrees of the vector field at these points. So, and this is a very easy calculation. So, okay, that's a good proof of this Gauss-Bonnet theorem using this theorem of Hopf and Poincare. Now, I will say that one could also have proved this theorem simply by triangulating the space, looking carefully at what happens to curvature and then flatten it out. So you have this sort of polyhedra that's flat, it has edges and vertices, and you look at what happens as that flatness develops. And you could have done it that way and gotten a formula that said faces minus edges plus vertices. But this is a pretty cool way to do it. Yes?
So with the proof that you outlined, is it clear that f does not blow up so fast as you go to the singularity?
It doesn't blow it up at all. F's just the curvature. See, F has nothing to do with the vector field.
I see.
F has nothing to do with the vector field at all. Okay? But, and of course, you might worry, but this, well, this is defined everywhere except there. But you can see that its differential at least is very well controlled, because its differential didn't have anything to do with those vector fields. So it's all okay. It's all okay. And you just see what happens. obviously, A, in order to integrate over something smaller and smaller and get an integer, A has to be blowing up somehow because, otherwise you wouldn't. You get 0 when you integrate around something teeny weeny. So A is blowing up, but dA is well behaved. So now we're going to talk about the generalized Gauss-Bonnet theorem. So this was a theorem that was more or less proved by Allendorfer and Weil some years ago. And so now I should point out that this Euler characteristic business is always 0 for odd dimensional manifolds. The reason is there's a duality that the ith Beatty number is always equal to the n minus ith Beatty number if a dimension is n. And so when you look at that alternating sum, it all cancels. But for even dimensional manifolds, it does not. So one normally looks at the Euler characteristic for even manifolds because otherwise it isn't so interesting. It's always 0. So, so now we'll have X compact, oriented, Riemannian, 2n dimensions. Now, we're going to look at SO2n, and it's Lie algebra, as a Lie algebra. I don't think I have to give this name. And we're going to look at a polynomial P, what I'm going to call it, P sub chi, on the Lie algebra, which is skew symmetric matrices, on the Lie algebra, which is invariant under inner automorphism. Such a, these are skew symmetric matrices. You could look at their determinant. You could do various things. But this one's called the Pfaffian, and I'll just say what it is as a polynomial. So this is a polynomial. So I'll say what it does when the variable is all the same. So if we look at P sub x, P sub chi of this canonical form, lambda 1 minus lambda 1, 0. Those are just little boxes here. 0, lambda n, minus lambda n, and 0 is everywhere else, right? P of this is simply lambda 1 times lambda n, just a product of those guys. And you can see that it's really the square root of a determinant, okay? This is a polynomial. I've just shown it in polarized form when I have the variable just repeated all the time. But it's a symmetric, that's what polynomial is, symmetric linear transformation from the tensor product of the Lie algebra with itself into the real numbers. There it is, called the Pfaffian. I won't write that down. And I'll write down this theorem without quite telling you what I'm doing. But the theorem is that I can, the integral over x, now I'm going to stick some curvature in. So P sub chi of f, bunch of f's, and n of them, equals the Euler characteristic of m, of x. So what I'm saying is take this polynomial, stick the curvature in a way I'm not going to really tell you, but stick n copies of the curvature tensor in, mush it all up, and you'll get a 2n form, right? You get a 2n form. You integrate that over x, and you get the Euler characteristic. And of course, in simply 2 dimensions, this is just the curvature itself. This is just just the curvature itself. Now, this theorem was proved, as I say, more or less by Allendorfer and Weil. I don't know if they had the whole thing. They did need to embed it in Euclidean space. There was a lot of work, and I don't think they proved it via the vector field method, but I don't know the answer. But they did sort of tortuously prove it, more or less. And I'm told, but not by Chern himself, but by someone, Chern and Weil got to be good friends shortly thereafter, and Weil urged Chern to look at this unattractive proof, which was not necessarily even completed or in all details, on all generality, and turn it into something simpler. And he certainly did. He certainly did. So what did he do? He turned it into really a one-pager, but sort of a one-pager. Let me find my one page here so I can tell you what it is. So he did this in 1943. And the name of the paper was A Simple Intrinsic Proof of the Gauss-Bonnet Theorem. And it was it's really a seminal paper, primarily because of the technique. So let's look at a bundle. Now I'm presuming a little more knowledge. With fiber, the 2n-1 sphere, and the going into the sphere bundle of x. That's a bundle of all unit vectors, the whole sphere over every point, maps down to here to x and the base. And I have my connection form A, connection. So this is a Riemannian manifold. Now, and this map is pi. Now, one can find a 2n-1 form, which I'm going to call T P sub chi, and it depends on F and A. I won't say how many copies of each, but there it is. Such that when this form is on the sphere bundle itself, on S of x, such that pi star, when I lift it, pi star of P sub chi of F's, I lift it up, it's the differential of, it's d of Tp chi of F and A, of F and A. So this form downstairs, which is a top-dimensional form, as it turns out, right, because x is 2n-dimensional, this form, when you lift it up here, is just a form. It's going to be closed because it was closed downstairs. If you lift up a closed form, you've got a closed form. But that it's exact is not obvious. And that there's a nice formula for what it's exact, what makes it exact, is not obvious. But there it is. It's a differential upstairs. And not only that, a very convenient fact is that the integral over the fiber itself, can you see down here? The integral over S2n-1 of T, of this thing, T, P sub chi of so on, equals 1. Equals 1. Okay? Now, here we go. We just start with a vector field downstairs. with isolated singularities. I can just almost just say this. So, but I'll sort of write it down here. So I'll take V, a unit vector field, unit vector field on X. So that with isolated singularities. Well, M sub I. Now, okay, so now I'll start out with trying to integrate over X P sub chi of F, of the F's. Okay, I'm going to try that. Well, I might as well just leave out the singularities. I don't add anything, don't have any measure. So that's equal to the integral over X just minus this bunch of mi's of the same thing, P sub chi, with the F's in there. Right? But over this downstairs, I can lift up to here because this is the vector field down here really defines a cross section in this bundle. So it's really a map from X up there, except at those little bad points. So I can say, oh, well, this is equal to the integral over what I'm going to call V star of, it's the push up of X minus the singularities of TP of the pull-up pi star of P sub chi of X, right? But up here, it's a boundary. So that's equal to the integral over this stuff minus these guys of d of P sub chi of d of TP sub chi, and that equals the integral of TP sub chi over the boundary of this thing, over the boundary of V star of X minus all its, those little points. Okay? Well, if you look carefully, the boundary of this is just a set of spheres. It's the whole sphere over the isolated singularity, because this thing comes into those points. It's all blowing up. It's not, but it covers the whole sphere. And in fact, this is really, it's really the integral over these spheres over the sum, if you like, as a cycle, over the sum of the degree of each mi times the sphere based at m sub I over the fiber of this TPX. But we just said, oh, when you integrate over a fiber, you get 1. So this is equal to summation mi. So now, you know, that I made it sound like, God, this is pretty simple. And in fact, it said, that was the title of the paper, a simple intrinsic proof. And it is pretty simple. But the level of sophistication that went into this, I think, had to have been considerable for the time. You know, what is a sphere bundle? I don't think everyone knew. It was just a lot about sphere bundles. What's a connection on a sphere bundle? How do you, you know, write the curvature properly? How do you? So all this stuff, which even physicists probably know today about connections and curvature and that stuff, and I'm not even joking. I don't mean to get a laugh, but physicists know about it. Yeah, nobody knew about that stuff, or very few people knew about it. So it was really a tour de force. And this theorem really led to a tremendous amount of mathematics, and it was a revolutionary. It was kind of revolutionary. Anyway, there it was, Chern's proof of the Gauss-Bonnet theorem. Now, this thing, this T_p chi, sitting up there in the sphere bundle, was really a forerunner. So T_p chi of F and A is a forerunner God, I can't spell it all. Well, never mind. Forerunner of this stuff, this Chern-Simons stuff, because it's one of those forms that turns out to be very important. So, I don't have as much time as I'd hoped I'd have. Can you guys stay another couple of hours? What's the...
Actually, we sometimes take a break after 1 hour. If you wish, we can take a break and then continue after.
All right. Well, I'm going to take a chance. So let's see what happened. I want to talk about the Weil homomorphism, the Chern-Weil homomorphism. So this is a big generalization in a way. So now we're going to look at a G bundle, a principal G bundle, E, over a space X. Again, with the connection, which I will, out of deference, call A. And the curvature F is equal to dA plus a half, or was it minus a, plus a half, A bracket A. In the abelian case, if G was a circle, A bracket A would be 0, and it would just, F would be dA. But in the general case, it's not abelian, and the brackets of this Lie algebra. So A takes values in the Lie algebra of G, and so on. So all this makes sense. And we're going to talk about IL of G equals invariant polynomials, all of them, of degree L, acting on Lie algebra of G. So this is, well, they're invariant polynomials. They're invariant polynomials under the inner automorphism action. And for any one of these polynomials, one can make, if I have such polynomial, I can make a form, P, and I want to be careful, it's going to be exactly LFs. So I'm going to use the curvature L times, contained in wedged 2L of the base. So it's a 2L form on the base. You can just, I won't tell you how to construct it, but you can do it. Okay. Now, the Chern-Weil theorem, homomorphism, says that, this is a theorem, it says, 1, that dP of F's is 0. It's a closed form. 2, the cohomology class is independent of A. Any old connection would have given you the same cohomology. And you know that cohomology is closed forms modulo exact forms, which is finite dimensional on a compact manifold. So the cohomology class is independent of A, and the map from P goes to the cohomology of P of F is homomorphism. In fact, it's a ring homomorphism. From, did I give this a name? IL. Oh, no, I didn't. Yeah, IL of G. Ring homomorphism mapping IL of G into the even cohomology of X with real coefficients. So this is great. Anytime you have an invariant polynomial on the Lie algebra of a bundle with connection, you get a cohomology class, and guess what? It didn't depend on the connection after all. But you got a nice form that represented it. Okay, that's I won't prove that. The proof is not terrifically hard. What you have to do is show when you vary the connection, there's a canonical way to make the difference of these two forms exact. So as you vary this depends on the curvature of the connection. You vary it, a form comes up that's also related to this CS stuff, and D of that form is the difference between these two things. And that proves that proves 2. 1 is just a calculation, and 3 is just a calculation. 2 is the guts of it, and it's not a very hard step. But on the other hand, again, when Chern and Weil did it, you know, it probably didn't seem exactly trivial. So, no, all of these are obstructions. They're called characteristic classes, and they're obstructions. I'm going to write all this down. They're obstructions to getting cross-sections in certain associated bundles over certain skeleta. In other words, lower dimensional parts of the manifold. For example, the Euler characteristic, you can get to anywhere in the even case except finally to the whole thing, and then you get stuck. You don't get stuck in any three-dimensional submanifold, let's say, of the 4 manifold. You could always get a vector field over that, but at a certain point you get stuck. And for doing all kinds of cross sections in these associated bundles associated to G, there are obstructions. They're called characteristic classes, and these represent, I think, maybe all of the real characteristics. They must represent all the real characteristic classes. Well, is that right? Yeah. So all of the real. There are some integer characteristic classes. Obviously, you can't necessarily get this way, and Z2 you can't get this way, but you get a lot. So let's just look quickly at examples of these polynomials, and then say it again.
What's the date of the Chern-Weil?
It's only a couple of years after 1943, I think. Jack, is Jack here? You don't know. Right, yeah. They were working closely together in Princeton.
So maybe right after the war, 47, 48?
Could have been. It could have been, yes. But I'm sure it was in the 40s. I'm sure it was in the 40s. And let's just look. If the bundle, if the group is UN, a favorite group, then the invariant polynomials I of UN is generated by trace powers generated by actually just the trace of G to the L. So you take a skew Hermitian matrix, raise it to the L power, take its trace. Every polynomial could be written, every invariant polynomial can be written by a linear combination. Well, not a linear combination, but anyway, sums of products of things like this. And in particular, you get, this leads to the so-called Chern classes. And if it's SON, it's also generated, here it's generated by trace of G to the 2L. Notice the trace of an odd product of G with itself an odd number of times is 0 because it's skew symmetric. It doesn't have any trace, but even traces, and that leads to the Pontryagin classes. So familiar classes for these two familiar family of groups, and if n happens to be even, you get one more, which is not a trace power, and that's that Pfaffian polynomial that I wrote down before. That's not a trace power, as far as I know, unless someone's very, very clever, but it isn't. Now, one important thing, and then we can move along. One important thing is the naturality. I'm very eager to get to the punchline here. One important thing is naturality. And it goes like this, that if you have one of these bundles with connection, E down to X, pi, and so on, G, well, I'm going to move it to the left here. E, pi, X, G. And then suppose I have a map, a smooth map of Y, some other manifold, into X. Call that F. Well, and then it turns out I can pull back everything. So over here there's another G bundle, principal G bundle, and that goes into what we'll call F star of E. And it has, and that maps down here to a pi. And there's the connection over here, and it pulls back to a connection F star of A. And here's the punchline of this, that if I take for a given polynomial P of F, an invariant polynomial, and I pull it back F star of this over here, that equals P of the pulled back curvature, in effect, of the pulled back curvature, P of F star of F star of F. So everything is natural in this business, okay? Push it over, pull it back, the polynomials, the forms pull back. So now let's do something funny. Let's pull a principal G bundle back to itself under the projection map. So let's use this neat fact about the thing itself. So here I have E goes down to X by G, etc. All very nice. And now over here I have E. And this was the map pi, and now I'm going to make this map, we'll call this map pi. So here I get G again, but here I get pi star. I think I didn't write, yeah, I did. Now here I'm going to get pi star of E, mapping down to E, and the connections and all the rest. Okay, now but a bundle, principal bundle, pulled back to itself is trivial, right? If you think about it a minute. If you, the fiber was the fiber below the point, this point is already in that fiber. The base is now the bundle, and I can say, oh, it itself is the base itself being a point in the fiber gives me a cross section in the pulled back bundle. So if you pull back a principal bundle or any bundle over the bundle itself, you get something trivial. And because it's trivial, this pullback, all the characteristic classes vanish because there's no obstruction to anything in a trivial bundle. And in particular, that means that when I pull back under pi, if I pull back pi star of one of these characteristic things, P of F, the cohomology class must vanish, and therefore it's exact, equals D of something, okay? It has to be D of something, and that something we're going to call TP of A and F. We'll just call it TP of A. So what I'm saying is I have a form down here, a characteristic form, P of these things. I lift it upstairs innocently. I just pull it up, and all of a sudden it cracks open and becomes exact. Just as in the sphere bundle, that characteristic form was open, was exact when we raised it up. We pulled it back up to the sphere bundle. That phenomena is very generally true. That when you, so now it's these forms that are interesting, and with a root of and I can write down the formula for this. In fact, I will, just so you can get a flavor of it. So TP of A is equal to the, well, it's a degree L, so degree L, you can integrate it. Integral from 0 to 1 of the polynomial itself with A plugged in and something called phi sub t to the L minus 1 plugged in, dt. So I have this sort of one parameter family of differential forms, and I'm integrating it to get a new one. And phi sub t is, what is phi sub t? It's t times the curvature plus t squared minus t times a wedge a, whatever exactly that means. So again, okay, so you do that, and now we'll look at one example where L is equal to 2. So if L is equal, here, I'll do it over here. If L is equal to 2, you get something it's going to start looking even more familiar. So for L is equal to 2, L equals 2. TP of A turns out to be P of A wedge F. Take these wedges with a grain of salt, minus 1/3 P of A wedge A wedge A. So now this is beginning to look like the classical form. So you can see that's just one example of these TPs, and there's a formula for all of them, and the polynomial is applied to all different combinations of A's and F's and so on, and with the coefficients in each place, and that's what that is. So now, when I came to Stony Brook here in 1968, I wanted to learn about characteristic classes. And I thought that a good way to do that would be to attack a problem, the difficulty of which I had no idea, and I didn't solve the problem, was to attack the following problem. The Euler characteristic is one invariant of an even dimensional manifold. But for a manifold of dimension 4k, let's say dimension 4, there's another interesting numerical invariant, called, I think it's called its signature. And it's when you take the two-dimensional cohomology, cup it together, you get a quadratic form on the two-dimensional cohomology of a compact-oriented four manifold. Just cup two guys together, you get a, and that quadratic form has a signature. It's a real quadratic form, so it has some positive eigenvalue. If you diagonalize it, has some positive guys and some negative guys. And that signature, the difference between the number of positives and the number of negatives, is a topological invariant, obviously, because it just comes from the cohomology. But it's not like just adding up the Beatty numbers or something. You have to do some work to cup and then calculate this quadratic form. So it's not a simple algorithm that just tells you how to do that. So I said, okay, I want to learn this stuff. I'm going to look at try to get a combinatorial formula for that form, for that index, by integrating what turned out to be a characteristic form, a well-known character, in fact, the first Poincare form, first Poincare class divided by 3, I believe, gives you the signature. So I said, oh, I'll just integrate that thing. I'll let it get corners and edges and faces. I'll see what the limit is, and there will be. I'll get a nice formula. Well, that did not work. It didn't work. It didn't work because there was this thing that I'll call a pesky term. So, and this pesky term, I couldn't figure out how to take the limit of it. So when integrating over this thing, as it got smoother and smoother, I had this sort of boundary of a vertex, of the star of a vertex, and a form in its frame bundle came up, which, not surprisingly, D of which was the Poincare form. I didn't quite realize all that at the time, and that form seemed very interesting. So I'm just going to write this down, and then I think so I'm going to have to stop, but we're kind of at the penultimate point. So this is now, so now we're looking, so then I decided just to study, see, by the way, this is a four-dimensional thing, and this is a three-dimensional boundary here. This boundary is M3, although it's really a sphere. But I got this term, and I decided I'd look at this term since I couldn't do any. See, it's a typical mathematician's trick. I couldn't make head or tails of it on the sphere, so I decided to try to make head or tails of it on any three-dimensional manifold, making the job perhaps harder, but on the other hand, there it was. So I said, okay, I have this form, which I'm going to show you in a minute, on this boundary. The form seemed to have interesting properties, I thought, so I was going to look at it. So here is the frame bundle of a three-manifold. So this is the frame bundle. We'll call it E again. Frames, and tangent frame bundle. And down here is a three-manifold, which I'm now going to call M3. And here is the Riemannian connection A. Okay, so that was my setup, a Riemannian three-manifold. And upstairs here in E, there was, well, there is. There's a, for the first Poincare class, TP1, and that's equal to 1 over 4 pi squared times, now I'll really break this up because this is just a skew-symmetric valued, matrix valued thing, and I'll write it in the way that I originally saw it. A12 wedge A13 wedge A23 plus A12 wedge F12 plus A13 wedge F13 plus A23 wedge F23. There it is. Now, D of this is supposed to be the Pontryagin form, but the Pontryagin form is four-dimensional. So D of it's going to be, it's a form up there, but it's automatically closed because D of it's going to be 0. So there's two important things about this TP1. D TP1 equals 0. And if I integrate over the fiber, which is really SO3, more or less, if I integrate over SO3, if I integrate even 1/2 of TP1, I get 1. Okay? So here's a closed form up here, and it's, when restricted to the fiber, it's an integral class 1. But M3, being a three-dimensional manifold, is parallelizable. You can always find a framing of it, at least if it's oriented. All three manifolds are parallelizable. So therefore, I could get a cross-section. So I could go up there and get a cross-section and pull back this. So I could integrate over M as a cross-section. Let's call it alpha. So I can integrate over M3 alpha star of this TP1 and get a number. Well, what would happen if I did a different cross-section? Well, let's just look. Remember, this is a closed form, so I'm just pulling this down. So here's one cross-section, and here's another cross-section. But they only differ homologically by a multiple of the fiber, which is SO3. They only differ homologically. So one of them could be written as, so if I looked at alpha, this is alpha, and this is beta. So beta equals alpha plus some number times the fiber. This is all homologically. So therefore, this integral is well defined up to an integer, right? Because the alternative would have been to integrate it over the thing too. I get n there. So if I reduce this modulo the integers, is well defined. So this is a function of a Riemannian three-manifold. Gives you a number. So we'll call it phi. So that, we'll just call this phi of M3 equals that. So it has two nice properties that were very useful. First of all, phi of M3 is a conformal invariant. That's one. And two, see how I wrote it down here. A necessary condition that M3 be conformally immersed in R4. So could you realize this three-manifold conformally R4 is that phi equals 0, or is congruent to 0. Now, any three-manifold is immersible in R4. But could it be conformally immersible? Only if phi is equal to 0. And here's a very nice example, the real projective 3-space, RP3. Phi of RP3 with its usual metric is a half. So here's RP3. Locally, it just looks like the sphere. It can be locally isometrically embedded in R4. Globally, it can be immersed in R4 because every three-manifold, but isometrically or even conformally, you can't do it. So this was sort of a very nice application of this form there, just in the tangent bundle of a manifold. Now, those forms exist for all principal bundles, SU2 bundles. They tend to be, you tend to get R mod Z invariance out of them because of the ambiguities. But as Witten cleverly did, he raised it e to the I, 2 pi I times this number, and then it didn't matter, up to an integer, you got 1. So that was all cool, and that became an action of which many of you are familiar. I've already gone 10 minutes over. I was going to write down what I just said, but there it is. So this is, anyway, how I got into this act and how I think these invariants, starting with some results like this, got taken seriously. That's it.
Any questions?
Some of this morphed into things called differential characters, which I did with Chi, but I was here. And in fact, it's this work that led me. If you look at this for flat bundles, you got some really interesting questions, and they have to do with whether certain numbers are rational or not. And I went for 2 years without any appropriate technology, not I think that it would have mattered, try to prove certain numbers were rational, and it drove me irrational. And I left and went into business and never turned back for quite a while. Any other questions? Anyway, I hope you're all having a good time at the conference. And all right, thanks for everybody.
Thank you.